Welcome to Lecture Online. In this series of videos, starting with this one, we're going to talk about the Kalman filter. Now, the Kalman filter is an amazing tool in order to estimate predicted values, but it's sometimes very difficult to understand how the Kalman filter actually works. So therefore, I made some videos to describe what a Kalman filter actually is, how to use it with some nice examples. So follow this. So what is a Kalman filter? Well, it is an iterative mathematical process. It's so you follow a set of iterations. It's a mathematical process that uses a set of equations. Those equations and consecutive data input. So we get a data input, we use the equation, we calculate the new estimate, we get another data input, we calculate the new estimate, we get another data input, we calculate the new estimate again. It's an iterative process. And the reason for doing it like this is so that we can quickly estimate the true value. So let's say that we have 50 or 100 data points that come in one at a time. And yes, we can do for example, a distribution of these values and find the average value and then say, well, the average value must be very close to the true value. But in order to do that, we need to have a whole bunch of inputs already. The Kalman filter doesn't wait for a whole bunch of inputs. It very quickly starts to narrow in to the true value by taking a few of those inputs and by understanding the variation or the uncertainty of those inputs, those data inputs. So it quickly estimates the true value, position, velocity, whatever it is that we're trying to measure of the object that's being measured when the measured values contain unpredicted or random errors, uncertainties, or variations as well. So remember that the data coming in is not the true value, it's somewhere around the true value with a certain amount of uncertainty. And of course, since that can bounce all over the place, it would be very difficult through any other system to try and figure out what the true value is or come very close to the true value. So a very simple example here in the graphical sense can help you understand that. Let's say we're trying to measure the temperature with a certain thermometer. That thermometer is not very accurate. It has a certain amount of uncertainty in the data measurements. Let's say that the vertical axis here means temperature, the horizontal axis means time or consecutive sample inputs. The little crosses here are consecutive inputs. So here the temperature is measured to be this high, then to be this high, to be this high, to be this high, then this. So you can see that the temperature measured time and again always varies because there's a certain amount of uncertainty in that temperature measurement technique for whatever reason it may be. And so therefore it would take a very long time for us to average these values out. The Kalman filter can do it a lot faster. It starts out by taking an initial estimate. It almost doesn't matter what the initial estimate is. And of course, in your estimate, you have to predict a certain amount of error or uncertainty. But very quickly, as data points start coming in and we go through that iterative process, the Kalman filter actually narrows down to somewhere close to the true value very quickly. It doesn't take very many data points to get there. And once you get there, as more and more data points come in, the variations will become very, very small. And the predicted value through the Kalman filter process will be very, very close to the actual temperature, in this case, in this example. So the estimated temperature using the Kalman filter will zero in and come very, very close to the actual temperature very quickly. Now, in this example here, there's only one measured value we're after, the temperature. However, this can be used, especially like in radar technology or GPS tracking satellites. We need to know the target that we're tracking. We need to know its position in the x direction, the position in the y direction, the velocity in the x direction, the velocity in the y direction. And yes, the Kalman filter can very quickly, again, through the very same process, narrow these intermediate values that come in, which can be all over the place because as you're trying to track airplanes via radar or targets via radar, you're trying to track satellites, that's not an exact science. The data coming in will have a certain amount of uncertainty in it, and the Kalman filter can very easily handle that uncertainty and very quickly zero in on the true position and the true velocity of the object that you're tracking. Of course, if we're looking for something like this, where we have multiple data inputs that we have to converge at the same time, it's a little different process than if we take a singular value like the temperature measured with a thermometer. What that means is that when we track satellites or airplanes, we'll have to use, instead of using a single number system and a simple set of equations, we'll have to use equations using of course, matrices, and we'll show you how to do that as well. But to get the technique down first, we're going to start with a very simple example like this, just simply measuring the temperature, and see how a Kalman filter, we can very quickly zoom in to that actual temperature that we're trying to figure out. And then once we have that technique down, then we'll expand it to the more complicated set of equations to be used to figure out how to track targets, like using radar, or how to use GPS tracking, tracking of satellites. All right, hopefully that gives you kind of an idea what a Kalman filter is. Of course, without showing examples, you're still a long ways probably from saying, oh, okay, I'm good with that, I know what this is. At least you have a conceptual idea of what a Kalman filter is. Now let's go practice with some real examples of how to do that so you get a very strong feel for what Kalman filters is and how to use them yourself.